Perhaps the most dramatic event that can occur in the universe today is a supernova, which is the explosion of a star that has reached the end of its life. While astronomers can see supernovas in their telescopes, researchers at Fermilab are building a detector that can see inside the core of the explosion. That just sounds kind of impossible, so let's see how it's done. There are several kinds of supernovae that can occur in the cosmos, and I don't want to describe all of them. One type occurs when a very massive star burns up all of its fuel, first converting hydrogen into helium, then when the hydrogen is used up, fusing helium, then carbon, and on up through heavier and heavier elements. Eventually, you can extract no more energy out of fusion, and the core of the sun turns off, so to speak. But then a funny thing happens. Without the nuclear furnace supplying heat to provide an outward pressure, the core of the star collapses, and just like in your car's engine, when you compress the gas, it heats up. That heat sparks one last flurry of fusion, and the resulting energy heats up the outer layers of the star, and the star blows up. The result is a flash that can be seen millions or even billions of light years away. Briefly, that single star will emit as much light as the entire galaxy in which it's located, and the galaxy will typically contain something like 100 billion stars. So that's an impressive thing to be sure, but what's even more impressive is that the flash of light that astronomers see in their telescopes is a tiny fraction, perhaps 1%, of the total energy released in a supernova. Most of the energy released in the supernova is in the form of neutrinos. There are reasons to be very interested in these neutrinos. For example, when a star actually goes supernova, it can take hours for the explosion at the center of the star to beat its way out to the surface and be seen as a flash of light. During that time, the energy interacts with the surrounding star, and therefore, when astronomers see the flash, they aren't getting a direct vision of what happened at the center. The flash has been changed by the interaction of the explosion with the surrounding star. On the other hand, neutrinos don't interact much. Thus, they leave the supernova pretty much unaffected by the expansion process of the explosion. It's not fundamentally different from how it works in our sun, in which the neutrinos created in nuclear processes at the center of the sun get to the Earth in about 8 minutes, while the photons take thousands of years to make it to the surface of the sun before they zip to Earth. So, is this all something we're sure about, or is it all theoretical speculation? Nope. We know this because we've seen it once before. Back in 1987, a number of detectors existed, built for the purposes of investigating the properties of neutrinos from space and investigating to see if protons decay. There was the IMB detector located in Ohio in the US, which consisted of a couple million gallons of ultra-pure water. There was the Kamiokande 2 detector located in Japan, made of about 3,000 tons of water. And then there was the Baksan Observatory located in Russia, and it consisted of 330 tons of liquid scintillator. One morning in February of 1987, over the course of about 13 seconds, these 3 detectors registered a total of 25 neutrinos. That might not sound like a lot, but it was way more than usual. And a couple of hours later, optical telescopes observed a supernova located in the Large Magellanic Cloud, which is a small satellite galaxy of the Milky Way located about 160,000 light years away from Earth. Astronomers eventually identified the progenitor star as a super blue giant called Sandelik -69202. This observation of neutrinos was the first, and thus far only, direct observation of neutrinos from a supernova. The supernova is also the closest one to have occurred since the invention of the telescope. Scientists were excited by the observation. It gave researchers a direct laboratory with which to test their theories of the behavior of matter at the center of supernovae. The second thing it did was set limits on the mass of neutrinos. The distance between the Earth and the progenitor star is about 166,000 light years. The neutrino release and light flash occurred within a couple of hours of one another, and the neutrinos and light arrived at about the same time, at least compared to the 166,000 years. Thus, neutrinos can't be very heavy, or the light flash would have outran them. And remember, the fact that the neutrinos got here first doesn't mean that they travel faster than light. It just means that the neutrinos escaped the explosion first. While Earth-based experiments give better precision, from this one observation, researchers were able to show that neutrinos have a mass less than 1/30,000th the mass of an electron. This was good stuff. Supernovae are pretty rare. Astronomers estimate that in a galaxy the size of the Milky Way, we can expect somewhere in the ballpark of 1 to 3 supernovae per century. That's rare enough that it might be hard to motivate building a neutrino detector just to look for supernova neutrinos. However, researchers are lucky. There are other reasons to build neutrino detectors, and astronomers interested in supernovae can piggyback on that effort. For instance, there is the Super Kamiokande experiment in Japan, which is a tank containing 50,000 tons of ultra-pure water. And the Japanese scientific community is building an improvement called Hyper Kamiokande, which will be 5 times bigger still. And, of course, here at Fermilab, my colleagues are building the Deep Underground Neutrino Detector, or DUNE. DUNE will consist of about 70,000 tons of liquid argon, and it's being built to study the behavior of neutrinos and antimatter neutrinos generated at Fermilab. I made a video about the DUNE experiment, and I put a link in the description if you want to learn more about it. Astronomers interested in supernovae are working with Fermilab physicists to make sure the DUNE experiment will be able to detect and record the neutrino signature of supernova. Unlike the event back in 1987, where 3 detectors were able to record a total of 25 neutrinos, if a supernova goes off in the Milky Way, both the Hyper Kamiokande detector and DUNE will expect to record many tens of thousands of neutrinos each. It will be a veritable cornucopia of neutrinos. And the 2 detectors aren't restricted to supernovae in the Milky Way. The detectors should be able to see neutrino pulses from galaxies as far away as Andromeda. Astronomers estimate that the Milky Way should experience a supernova every 50 years or so. But statistics being statistics, that could mean the next one is tomorrow, or it could be a century. The last confirmed supernova in the Milky Way was observed back in 1604. So if you believe the rate of supernovae estimated by astronomers, then it would seem that we're due. It turns out that while 1604 was the last supernova that people observed, researchers have found evidence for more recent ones. For example, we now believe that Cassiopeia A exploded 325 years ago and nobody saw it. This is because a supernova often occurs in the disk of a galaxy, which is where there's lots of dust. That dust can block the light from supernovae, which is why we don't always see them. But the dust won't block neutrinos, so DUNE and its cousin detectors will be fantastic laboratories to look into any supernovae that can happen. I can't predict when the next supernova will occur. Nobody can. There was some hype in the media a couple years ago that claimed that maybe Betelgeuse is about to blow. Betelgeuse is a red supergiant star about 550 light years away. If it did go supernova, the signals in the DUNE and the Hyper Kamiokande detectors would be nothing short of spectacular. Unfortunately, most astronomers believe that the hype in the media was just that, hype. The date expectation for Betelgeuse going supernova is still 100,000 years in the future. But don't be disappointed. There are at least 200 billion stars in the Milky Way. One of them is bound to blow on a reasonable timescale. And when it does, neutrino scientists will be able to tell us a ton about one of the most spectacular explosions in the universe. They'll be waiting. Okay, so that was pretty cool. Well, I'm a physicist by trade. I loved astronomy as a kid. Space is totally fascinating. If you like learning about how we can get a new perspective on how stars explode, well, you know the drill. Please like, subscribe, and share. And you got to do it, because if you're sharing, you're telling your friends about some awesome physics, and that's why it's important, because, well, physics is everything.